Welcome everyone to this first episode in a series exploring the development of the Tidal Emergence model of cognition and its implementation in TE-Sim, a fully interactive simulation environment. My name is Michael Snoswell and I've spent the last 4 decades working in IT, from software development to solution architecture, mostly on real-time military systems. I've designed and built machine learning and AI systems. My first attempts were way back in the early 80s, up to a full 3D multi-user interactive virtual world called Cyberterm in the 90s, which embodied self-directed independent agents that roamed through the servers, interacting with each other and users. I've also studied psychology and am a qualified psychotherapist or counsellor with about 20 years of experience there. Overall, I have a keen interest in how we think, how our minds have evolved, and what is the quintessential nature of self-awareness. I've always paid attention, particularly to the evolving models of consciousness, since it really took off in the mid-90s, with a particular focus on models that can actually be implemented in software. I was impressed with Michael Brook's Jengus robot that taught itself to walk, and to Ben Goertzel's Cogsheep, and with many other attempts to embody consciousness models modelled on biological systems, but created in software and machines. So my journey in AI has been unconventional, but it's led me to a model that I believe is fundamentally different from traditional approaches, the Tidal Emergence model. Now, in this series, I'm going to take you through the concepts, the technology, and the development process behind TE. I'll explain why I believe existing models of consciousness are incomplete and how TE is designed to bridge that gap. And along the way, I'll show you the code, the simulation environment, and the challenges of building an evolving, feedback-driven cognitive system from the ground up. Today, I'll start with 3 main topics. Firstly, my journey from the early AI projects to the development of TE-Sim. Secondly, the core concepts behind the Tidal Emergence model, including ProtoMinds, ComparatorMinds, and memory bundles, which are key elements. And thirdly, I'll take a look at the current state of TE-Sim. It's a work in progress, but I'll show what's working, what's next, and the long-term vision for this ambitious project. And by the end of this video, you'll have a clear understanding of how TE-Sim came to be, why it's different, and where it's heading. Now, let's get started. I started programming back in the early 80s, around the same time that personal computing was really taking off. I wrote my first AI program in about 1982 using Compass Pascal on a CPM machine. It only had 64K of memory based on an Apple II computer with one of those Z80 cards into it. And as you might recall, Compass Pascal was later bought out by a company called Borderland, who renamed it to Turbo Pascal. My system was called SLAI, SLAI, Self-Learning Artificial Intelligence. It was an ambitious goal, but it used letter frequency and analysis of statistical tables using analysis of text to try and determine and predict the next letter based on the context. And that experience really sparked my fascination for how machines could learn and adapt. And as you know today, our LLMs use almost exactly that same model, except it's based on words rather than letters. I was a little bit before my time and in slightly the wrong direction, but it was a good start. Well, Cyberterm was a 3D virtual environment I created starting in the beginning of the 90s right through to early 2000s. It had autonomous agents that could navigate through the 3D world and learn from their environment, and even interact with users in real time and transport themselves between servers. It was a multi-user engine, and a number of the agents were programmed with genetic algorithms that were written in TCL. The underlying engine was written in C. Now, looking back, it was a primitive form of what we would now call agent-based modelling, and it taught me a lot about emergent behaviour. The real takeaway was how complexity and adaptation can arise from relatively simple sets and interactions. I spent about 2 decades as a software engineer, writing code, building systems, running projects, and eventually I transitioned into management and project management, which gave me a deeper understanding of large-scale system planning and execution. But the itch came back to AI, and it never really went away. When I started thinking about consciousness modelling, it was like everything that I'd worked on before came full circle. I tried to write neural network programs back in the 90s, written from scratch in C based on articles that I'd read in magazines. And this had given me a fundamental understanding of what people at the time were calling AI, and even today call it that. But those in the field know that artificial intelligence is a long way away from what neural networks and LLMs can do. But TESIM now is a result of decades of experience applied to one of the most challenging problems: modelling cognition and consciousness. Look, the main gap I saw was the lack of some dynamic, feedback-driven system that could evolve ideas over time without hard-coding behaviours. Models like the global workspace theory or attention schema theory are conceptually sound, but they don't fully address how multiple competing thoughts are handled in real time. They're ideas or conceptual models of how things might happen, but there's not sufficient substance to actually be able to implement a system. And there's just lots of problems in there that I could see as a developer trying to or wanting to build a system that works. So that's where this idea of ProtoMinds came in, which is a core part of the Tidal Emergence model. They're modular, evolving cognitive units that can be created, modified, and deleted on feedback from the environment. They're not software controlled in how they behave. They're completely autonomous and self-driven as how the system runs. So Tidal Emergence is fundamentally different because it's not about simulating human cognition as such, and it's not about modelling from the neuronal level. It's about modelling how that initial proto-conscious system might evolve and adapt over time, with a lot of attention on the evolution of mammals over time and how they think, also looking into avian cognition and things like octopi, which appear to be conscious as well. But then also the development from a newborn child through to an early childhood, where, having had kids, you'll know, you can see the thoughts and the awareness actually develop before your eyes, which is just fascinating. And I'm constantly referring back to that when I'm developing my software and trying to work out what features to add next. So a core concept of that also is called memory bundles, which influence future decisions and store data. And that comes from a lot of my counselling work, where working with people and the models of Gestalt therapy, where there are scripts in people's minds which they are often not even aware of, that are replaying old memories which play out in their current day life or influence their current day life. I wanted a model that could capture that and be a little bit more true to the real world understanding of how the human mind works. And this system is also evolving. From the moment you start the software up, it is very simplistic. In fact, it can't do anything. It needs to interact with the environment to build up its complexity and its memories and its ideas and its internal processes, which just increasing complexity over time as it interacts with itself and the environment. So it's quite complex from that point of view, but it is not guided by a rigid set of rules of how it should behave, how it should evolve, or how memories are actually put together. Well, ProtoMinds are these independent cognitive units that they generate behavioural ideas, and ideas always come with an emotional content and a goal. And there are many ProtoMinds, and they semi-autonomously propose potential actions for the body to undertake with the external environment, and there is a emotional influence on these. There's also a goal which they are seeking, which influences them over time. So and based on the feedback from when those ideas are executed in the environment, that will reinforce or inhibit those initial thoughts. So there's a memory about a potential action which can either be reinforced if it was successful with positive feedback, or would be inhibited. So there's a number of proto-minds in the model that together produce a wide number of random ideas effectively to start with. These ideas are passed up to a comparator mind, which examines these ideas, and based on the current goals of the body, for instance, if there's insufficient food or if the body is cold and a number of other attributes, the comparator mind will look at those ideas and determine which one is the best at that moment in time. And I currently run the simulation in a real-time mode. I don't let it run flat out, which it certainly could on a computer. So you can watch those thoughts rolling around and data up on the screen in terms of which get selected, which don't get selected. And the comparator chooses what action, because the body can only take one action at a time effectively, and it makes a decision and then passes back the results of those behaviours. So when behaviours get executed, their outcomes are then stored as what I call a memory bundle, which is a bundle based on my counselling work, where I observe that when people have a memory, it is always associated with an action that happened at the time, with their thoughts at the time, and with an emotion at that time. And to interact with that emotion, some people are better at using emotions, some people are better from the cognitive point of view, and some people are better using behavioural or body-based aspects to bring up those memories. It seemed to me quite natural that any memory must have these three key attributes tied to it. So the tide concept is about accessibility of the conscious mind to these particular memories. The memories can accumulate below a level where people are not aware of them. They might have quite a strong, for example, emotional component, which can cause them to trigger, and they might trigger at a level that is below the awareness, and I call that being below the tide line. But the tide line isn't actually a fixed thing, which is why I call it the tide. It's not a hard line, and through psychotherapy and counselling of sorts, people can actually expose those memories from the past for a while to work on them, to mitigate them, to understand them, to lessen their effect. And if they don't do that, they sit there below the surface generating outputs that impact on your day-to-day behaviour, often in ways that people are not interested. So the idea is that the tide can lower, work on some things, the tide goes back up. Everything above the tide line is consciously accessible. Below the tide, they're still running. There's little scripts there running on memories and doing things which are not directly accessible to the consciousness, and I wanted to simulate that. So tidal emergence is, as a model, does a number of things. Because the proto-minds themselves evolve based on the feedback that they get, the idea is that there would be many layers of proto-minds. Some pass up very simple ideas, but as it passes up through the levels, the ideas become more complex, and each proto-mind itself is almost like a comparator in that it will look at ideas that get passed up from earlier, come up with its own ideas, put together ideas, and each idea, as I mentioned, is based on a goal, emotional state, and an action. And these can be combined, and when the results come back, you might get a result that comes back that actually has many steps, and there's a concept of memory bundle chains. So there's chains of actions and emotions and results that occur. So as you can probably tell already, that this model mirrors biological processes in many ways. But the proto-minds are not like individual bundles. They're actually, well, memory bundles. They're not like individual neurons. And the memory bundles resemble in some ways the memories that are stored in synaptic traces and weightings. It's not quite the same. I'm working at a more symbolic level. So we do not have to have, if you had a full simulation, you're not going to have billions of proto-minds, because they are symbolic and manipulate symbolic data. Whereas the comparator mind at the top is effectively the decision making cortex at the top. So TE-SIM is currently in an early stage of simulation. I've worked on a paper I'm putting together for describing the tidal emergence model, but I got excited about it. I could really see some potential here, so I started implementing this, and with my software background and looking at a lot of other systems that people have tried, I could see what really was a clear path to go down, and that path, I believe, is a path that nobody has trodden before. And I'm already getting some interesting results out of the system. It's implemented in Python. There's a number of classes regarding, like, for instance, the animal, which is the body, and then there's a mind class and a comparator, and there's proto-minds. Certainly the biggest challenge so far has been synchronizing these, because I don't implement these as a lot of simulation models have some lockstep clock that ticks along and everything updates and updates, and I'm very familiar that it's a standard way of doing simulations, but that's not the way the mind works at all. Everything's running at the same time, all asynchronously. You've got little thoughts running around in the back of your head, and some occupy quite a bit of space and time, and others are going quite quickly, some are going slow, some have strong emphasis, some less. So what I've done is implemented all of these as completely separate threads, not processes, but separate threads that all run asynchronously, and over queues they send messages through to each other and communicate that way, much like that in the brain messages are sent over dendrites and synapses. So I've got cues that send data backwards and forwards. I think that is going to be a key element that differentiates what allows the emergence of, how should we say, interesting and complex behaviour. So the way that the ProtoMinds interact with the environment is they generate ideas which go up to the comparator, and then the comparator then works out what should do. So for instance, it's the body temperature is cold or less than optimal. The comparator will tend to favour behaviours that either in the past or random new, but have something related to temperature or movement or something like that. So there's a lot of filtering and things like that happen that level. I don't program the filtering in. It works out based on, as it evolves, what is best to filter and what works and what doesn't work. And then there is an action or a behavior which is then selected, that then gets sent to the body, the animal, which in the virtual world then either moves on the screen or changes on the screen, and then feedback is results, which is then sent back to the comparator, which can then effectively keep track of whether that was successful or not. So those behavioural inputs are then handled by this animal class, which detects the changes in the environment, location, satiety levels, and routed back to the results, are routed back to the ProtoMinds, which, if they're reinforced, they are likely to generate more ideas based on something similar. And if they were got bad feedback, they are inhibited, and in fact it even gets to the point where if a ProtoMind has generated too many bad ideas, it will get deleted. But it could have had a whole, imagine a ProtoMind had 50 different ideas over time, and one which is really good. That one is actually kept and is handed to a new ProtoMind, and so it starts with a memory or a memory bundled chain of things which encapsulate what the original idea was and what the feedback was, so that new ProtoMind can then start. And I thought perhaps this might emulate what happens in the human mind from a baby as they're evolving, and your brain is certainly not pre-wired. There's functional structures in there, but at a very macro scale. But on the neuronal level, there's just a massive over abundance of neurons and dendrites which undergo pruning, for the first 5, 6, 7, 8 years of life. So I wanted something that, from a conceptual point of view, can also do the same. The next phase, I'm going to focus on expanding the environmental complexity of the system, introducing more sophisticated inputs, adding more details to the ProtoMind selection process, and also refining. I can't overlook the fact that humans and everything that thinks has some innate drivers, which are effectively manifest as behavioural drivers. So there will be certain kinds of ProtoMinds that receive inputs from innate drivers, which are necessary to function. And I believe, just I get a feeling that they'll be a key part of the future correct functioning of the system. And a lot of that internal feedback data goes on to what I call the wall at the moment, so that any thought, any idea, any ProtoMind, any memory can have access to key overall data about the state of the body. Well, in the long term, I would really like to at least complete all the features that I've got planned to implement. I've implemented perhaps a dozen features, which are key elements of the tidal emergence model, but there's many more that have come to mind as I've done this, about distributed memory and implementing features that are similar to the gamma waves, the 40 hertz odd, that travels around the brain, which is thought to be a key element of memories. And I've come up with something that I think is going to work for implementing something similar, which will have a significant shift in that memory becomes effectively computational, and is fundamentally different to anything that I'm aware of at all. I certainly want to introduce ProtoMind hierarchies, and the ability for my simulated mouse to interact better with the environment, and perhaps to have a simple mazes to work through to see if it can develop a memory for going through those. And the end goal is to add to the complexity of the system. I don't believe it will be conscious or self-aware. I won't know exactly if it is, because at this stage I'm not planning on giving it language at all. That would be most artificial to do. I don't want to presuppose any concepts about our current minds and how they work and impose that on my model. And I've come up with a mechanism for making sounds and listening, which will be completely how can we put it, based on emerging behavior. So it will evolve its own speech or sound making patterns and listening, and of course one of the later features I want to have multiple ones of these mice running, interacting with each other. In the end, if my goals of features are fully fulfilled, there will be they might interact with each other and communicate, and we won't understand what they're saying, and effectively we'll have to analyze the sounds that they make to try to determine their actual meaning that goes backwards and forwards, because I am not telling it how to think, and I'm not putting words on different aspects. It purely evolves all these features itself, which will be great. So I'd like to thank you for joining me on this deep dive into the tidal emergence model and its implementation in TE-SIM. In this first episode, we explored the origins of the concept, its foundational ideas, and how it differs from traditional AI and consciousness models. We also looked at the current state of the TE-SIM, the many challenges that are faced, and the exciting roadmap of just some of the features that I'm looking to implement ahead. If you found this interesting, do make sure to subscribe to the channel, and I'll be documenting my development process, my joys and my failures in that, along with live demonstrations of the system as it evolves. I'd love to hear your thoughts and questions in the comments below, especially if you're working on some similar concepts or exploring AI and consciousness yourself. In the next episode, we'll take a deeper look into the ProtoMind evolution and the adaptive learning process, how TE-SIM actually generates behaviours, evaluates outcomes, and iterates on its own learning without any pre-scripted rules on how to do this. I'll also share some of the live coding sessions. As I build out the next phase, you'll have to bear with me on that, but I see many future sessions talking about this. There's enormous depth, and there's also a lot of reasoning into that's gone into some of the features that I've already implemented, that I plan on implementing. I'd love to talk to people about their thoughts on some of these ideas and the current performance and maybe some future concepts. Thank you for watching. I look forward to continuing this journey with you, and until next time, stay curious and keep questioning.